Hi, I'm MC. I'm here to talk about how to verify a Tillitis TKey. I'm a member of the technical staff at a company called Tillitis, and this is me hugging a computer terminal, as you do. You can find the Tillitis company at tillitis.se and myself at hack.org/mc and my Gemini capsule, of course. Tillitis, the company, was born out of the trustworthy computing research team at Mullvad VPN, and as you can see, this is Cookie, the mascot of Mullvad, building some kind of hardware. The research department split into two companies in September 22, and the hardware department, that's us, that's Tillitis. We build this thing. It's the Tillitis TKey, an open source, open hardware security token. The large chip you see behind the ant is an FPGA chip, and our design is inside that FPGA chip. The Tillitis TKey is an open environment for sensitive computations. It's basically a RISC-V computer with some interesting hardware features in a USB stick form factor with no persistent storage. It uses measured boot to create unique identities based on what the user has, the actual hardware they have, something the user knows, typically a passphrase, and the integrity of the software that runs on it. Everything is released under open licenses, including the hardware. It's available on our GitHub repos, and you can read about how to develop apps for this thing on our excellent developer handbook. Inside the FPGA, we have a RISC-V CPU soft core. We have some RAM. We have some security hardware cores that are memory mapped for ease of use from the CPU, from your own apps. There are different CPU modes that we added, which basically means that some parts of the memory map isn't available anymore in the app mode. We also added an execution monitor, which basically means that you can turn off execution from some parts of the memory, just like in modern processors. We have supporting Clang and LLVM, which means we, for now at least, write things in C. There's been bring-up attempts in Zig and Rust, but we provide a lot of libraries to support C development right now. And some third-party people did the same thing for Rust. There's no storage on the TKey itself and no operating systems, but as I said, we provide some C libraries. You can use the TKey as a second-factor authentication token. You can use it for digital signatures, as a hardware root of trust in a larger system, as a hardware random number generator, even signed if you want to, which means you can prove where your numbers came from. You can use it for encryption and protected environment for sensitive computations because it's a general computer. You can do whatever you like with it. A typical use is like any other security token. You insert the TKey into your client, and the client here, that's what we call a mobile phone or a laptop or something. You want to access an SSH server, so you run your SSH command, and the TKey is automatically loaded with the necessary app to do so, the app that provides the authentication. The app now blinks the status LED, and you touch the touch sensor to assert presence, and you're in, just like any other security token. However, this thing is a general computer, not like a security token at all. So, if you can send whatever app you like to this token, to this computer, how can you trust it? Won't it leak private keys? What about any hardware keys? Isn't that available all the time? How can you trust something that is a general computer? First, what if we don't share anything between the apps running on it? And the only way to start a new app is to remove the TKey from the client, forgetting everything, and then inserting it, hopefully, and then inserting it again to start a new app. No storage, remember, so there's no state persisting between power cycles. And what if we also guarantee the software integrity of the software running on the TKey? We use measured boot to ensure the software integrity. We measure the application, mix in a hardware secret, and get a new identity. This is inspired by the DICE project, which was originally called Riot from Microsoft Research. Great name. The advantages of using a measured boot is that software integrity is guaranteed, and this measured identity can be used to create key material that you can later use. Any private keys generated are not stored persistently, and since there's nothing to store, you can create any number of private keys. And the secrets, as I said, don't leak between applications. This is different from verified boot or secure boot, as it's called in the PC world, where instead of doing a measurement, you typically, most often, demand that all applications are signed and that you control the signature before starting anything. And this is unacceptable in our case because we don't want to lock down the TKey to accept just apps from one vendor. This is meant to be an open platform for doing sensitive computations. So instead, we use measured boot, which is a generalized way of creating identity. What's this identity I'm talking about? We call it the compound device identity. It's a cryptographic mix of something in the hardware, the unique device secret, something the user has, that particular TKey. An optional user-supplied secret, which is typically a passphrase or a file from the keyboard or from some random data on the client, something the user knows. And then the measurement, which is a hash digest of the TKey device application before it starts. It's loaded by the client into the memory of the TKey before this first instruction is executed. It's measured by the firmware, by the bootloader. And that is the integrity of the application. So we do a hash function called Blake2s over the entire application in the memory. Now we have a digest of the software integrity. Then we do another Blake2s over the unique device secret, the digest of the application, and any USS the user has entered. This is the compound device identity. Remember this is important. The supply chain of the TKey is that we get PCBs assembled in Sweden, and when the PCBAs end up in our Gothenburg office, the FPGA is empty and unlocked. And then we provision the bitstream, the hardware design, into the FPGA chip and lock it down inside the configuration memory inside the chip. We lock it down by blowing a fuse inside the chip, which makes it impossible, or at least very hard, to read it out again. Inside this FPGA bitstream, the entire firmware, the bootloader, is a part of that. It's a part of ROM in the bitstream. And then the hardware secret, the UDS. So this is important that an adversary can't read it out again. And so to guarantee the supply chain, we also, to the end user, we provide user-verifiable firmware and identity, which is the rest of this talk is about. So we offer users the ability to verify that the TKey identity that we saw during hardware provisioning in our air-gapped environment in Gothenburg is still the same when they receive it in the mail, or at any time later they want to see that nothing has been changed. This leverages the measured boot system I talked about earlier, and then we publish a verifiable message containing proof of the device identity that we saw. This, however, is only for the pre-provisioned version of the TKey that's available in our shop, not for the TKey unlocked. The TKey unlocked comes with an empty FPGA and is meant for someone who wants to choose their hardware secret themselves, or if you want to write some Verilog. That's when you buy a TKey unlocked. In all other cases, please buy a regular TKey, and then you can verify it like this. Let's get into some details about doing this verification, both how we do it on our provisioning side and how you as a user can do it on the user side. Let's start by introducing the signer. The signer is a device app that does elliptic curve signatures. You can see its GitHub repo here. And when you start this app on a TKey, it starts by creating a key pair based on the compound device identity, the measured identity. It has a protocol for things like extracting the generated public key, signing a message, and computing a digest over the firmware. That's what we need in this case. So in our Gothenburg office, when we have received the TKey PCBA, we have inserted the entire FPGA bitstream into the FPGA chip, locked it down, then we do this. We run a program that extracts the serial number, the unique device identifier, something that uniquely identifies this particular device. That's not a secret, and it's available from firmware. Then we load the signer app I introduced, extract the public key, do a challenge response to verify that it has the corresponding private key. This means this TKey is not trying to impersonate something. It actually has the private key because we can verify it. Then we request a hash digest over the entire firmware from the app and create a message. We sign this message with a vendor key and publish. This is wrong. We publish the signature and some metadata indexed by the UDI. So now you can find this signature and this metadata on the web indexed by the UDI. This signed message, not what we publish, this is a message you can recreate. This is the unique device identifier, the firmware digest, and the public key of the signer on that particular TKey. And again, the app's key pair is based on the hardware secret and the app measurement. This means that this key pair is unique for this combination of this TKey and this app. So the signed message is a proof that we ran this particular app on this particular device. And this message is not published, but can be recreated. When the user gets the TKey in the mail, and they are afraid that the NSA or Mallory, whoever, interdicted the package, did something with the TKey, replaced it with an almost lookalike TKey, and you want to make sure, you'd run a program called the TKey verification with the verify command. And it looks like this. If you run it, it says something about the serial number and the product ID, et cetera. Then it says TKey is genuine. And it's been verified with this vendor key. That's basically it. It can be done offline, so this program, by default, goes to our website, uses the UDI, and fetches the verification data. But if you have an offline environment, you can do this manually and then securely transfer this verification data somehow to your offline computers and run a slightly different command to do it there instead. So what happens when you run this command? First, we request the unique device identifier from the TKey. That's from the bootloader, not secret. We fetch the verification data from the web, which is indexed by this UDI, the serial number. Then we load the signer app, extract the public key, do challenge response again, just like we did during provisioning, to verify that it has the corresponding private key. So now this TKey is not trying to impersonate something. Then we request a hash digest over the firmware, or at least from some memory parts that we think is the firmware. Then we have the possibility to recreate the message with the UDI, the firmware digest, and the app pub key. And since we already fetched the verification data with the signature, we can verify the signature over this message. And if it verifies, we have proof that this was the same app that was running on this TKey during provisioning as it's running right now. The verification data that we publish looks like it contains the timestamp and a name and tag of the signer and the hash digest of that particular device app, and then the vendor signature of the message. We don't publish this. We don't publish the actual message. We publish this verification data. And this app tag thing, that's mostly for humans because we use the app hash in the program to find the app to load. It looks like this on the web. When we run this, what has been proved? We have proved that the same thing we saw during provisioning was the case when the user ran it, and that is the unique device identifier of the TKey, the serial number. Then the app's key pair was the same, and the firmware was the same. And the same key pair, that proves that the compound device identifier was the same, which proves that it was the same app that was running. And that proves that it was run. Also, it proves that that was the same unique device secret in hardware. Remember this, I said it was important, which means we have proven that this particular TKey was running this particular app, even in our Gothenburg office, as you are running right now when you verify it. That's the entire reason to do this. Less strongly proved is the CPU. We could run the program, the signer, right? And that's okay-ish, but we can't prove that the CPU hasn't been tampered with. We can't prove the rest of the FPGA design either, except the UDS. That's proven. And the rest of the PCB design is not proven either. So imagine a naive user. They get a TKey and they want to verify it. They search on Google or DuckDuckGo or something and find the TKey verification program from a site called evil.com. And then they download the TKey verification program and run it just like that. And that program, it just says, the TKey is genuine. This is, of course, a problem. But this is the same problem that everyone else has. Who do you trust when you install programs? So we release binary releases and reproducible builds of this program ourselves as GitHub releases. We insert it as much as we can into regular distribution channels, Linux distros, Homebrew, Winget, etc. We try, but we're not quite there yet. So right now, if you download a binary from wherever, don't trust it. But if you download it perhaps from our GitHub releases, you can trust it a bit more. And what's more, it's open source. You can download the source code, you can compile it, and the entire spec about all this verification process, everything is published. So if you want to recreate this and just pick the public key that we published through a secure channel, then you can do it yourself. Anyway, this is the weakness even in verified boot and in secure boot scenarios. This is not particular to us. This is a problem everyone has. But in this case, malware at least needs to attack multiple places at once, interdict your package, replace it with something else. Then when you are going to download the TKey verification program, they have to know that it's you and replace that program with their program. This is harder to go unnoticed, so this might just be helpful at least. The device verification infrastructure is up and running since March 23. So this has been running for over a year, and all the current TKeys can be verified like this. We will keep it running, of course, but we will also work on it. And we are currently working on a new TKey generation with persistent storage. This is kind of hard to do securely, so let's see where that goes. But if we do, perhaps we can store the verification data there too, and then you don't have to use the published thing on the web anymore. Perhaps. And then we might want to use one of our sister companies' transparency log projects, the SIGSUM project, to store some things, like the digest of the TKey verification program we released, for instance, and perhaps the vendor public key data, a digest of it, and etc., etc. So in conclusion, we have a solution for an open device verification for a general computer without locking down the device and leveraging the TKey measured boot system, which can be used anywhere else. If you want to find us, you can see the webpage on tillitis.se and shop.tillitis.se to buy TKeys. And then there's our helpful developer handbook if you want to develop your own apps for the TKey. And we are on IRC and Matrix. And remember, this is open source projects, so please help out. Thank you.